All right. So before lunch, we got down to this relation between x and y, and we want to know for what values of x and or y is this relation true. This is going to be, again, as I was mentioning, a pretty typical scenario when you have these types of problems that come out of implicit differentiation. On the problem up here when we had the circles, notice we were able to set it equal to 0, and we had numbers, okay? But most of the time, you're going to end up with two variables. So what you do then is you solve for either one of the variables, whichever is easier, it doesn't really matter, and then you plug back in to the original expression which relates x to y. So if we do that, we're going to get negative 3/4 the quantity squared plus y squared, or that's 3/4 y, sorry, there we go, equals 4. And if you carefully square negative 3/4 y squared, you get 9/16 y squared plus, I'm going to go ahead and call that 1y squared equals 4. And now if you notice, we have like terms. It's kind of nice that they're both squared. So 9/16 plus 1, 1 being what, 16/16? So 9 plus 16 is 25/16 y squared equals 4. And I think you can see that we're gonna make it. We're gonna be able to solve. If you multiply both sides by the reciprocal, you get 4 times 16/25. And of course, now if we take the square root of both sides, notice that we have 3 factors there. All 3 are perfect squares. That's kind of nice. So we'll just take the square root of each and multiply them together in the end. So the square root of 4 is 2. The square root of 16 is 4. And you can say it's all over the square root of 25, which is 5. And nothing divides out, so you get plus or minus 8/5, which is the same as what as a decimal? 1.6, yeah. Multiply by 2 over 2. So what does that mean then? We know that the y value is 1.6. And what did it ask us for? Well, I always want to make sure we answer the question. At what values of x? Well, I got the y values. So to get the x values, I guess I can plug it back into which equation? Do I plug it back into x squared plus y squared equals 4? Or can I plug it into this one as well? Yes, you can plug it into either one at this point. I think the one on the left here is going to be easier. So x is going to equal negative 3/4 times y. And I'm going to use the 8/5 version here. And when I do that, the 4/2 divides out, and we end up with negative 6/5. So I got that x value, and essentially the point is going to be now negative 6/5 comma 8/5. Even though they didn't ask for the ordered pair, they just asked for the x value. What would the other ordered pair be, based upon our little diagram up here? If one's negative x positive y, the other one by symmetry should be the positive x negative y. Bless you. Yeah, and you could verify that if you plugged in the negative 8/5. But the other point's going to be positive 6/5, negative 8/5. So to answer the question, the x values could just be plus or minus. And there you go. That's it. Now there's one other thing that you could have done here, and it would have saved that very last step. If you knew that you were going to be looking for x values to begin with, you could have taken this little proportion right here, and instead of solving it for x, you could have very quickly solved it for y by multiplying both sides by the reciprocal. And now if you would have plugged that in over here, you would have had a function of x, and then you would have gotten your answer down here. But it's not a big deal. If you solve for one variable or the other, you're going to be able to find the one that you need. Okay, so again, just make sure you're answering the question that's actually being asked. Don't just stop as soon as you get an output. All right, you ready to try it again? This one was a circle. It was nice because we can kind of, validate the answers. Now we're going to have an equation of something that looks kind of circular, right? Maybe the layperson calls that a circle because to a layperson, maybe everything that's round is a circle, right? But it's not a circle. Maybe someone who's more astute would call it an oval, right? But we math people call it an ellipse, and we're proud to call it ellipse. This is a rotated ellipse, okay? You probably studied ellipses in Algebra 2, but you probably never studied any conics with an xy term in it. The xy term is what's responsible for the twist. But I think you learned that if the coefficients of your x squared and y squared were the same sign, but different numbers, those affect the x radius and the y radius, so that ends up being an ellipse. If those numbers were the same sign and the same number, then your x radius and y radius would be the same, and you'd have a what? Circle. And if one was positive and one was negative, you'd have that other one that's the, not the Heidi-ho, but the hyperbola. Hyperbola. Yeah, Hody-hi. It's the Hody-hi rule. Yeah, let's not even, I don't want to say Heidi-ho. Hody-hi, right? Okay, so here's the graph, and here's the equation. It says, part A, determine the x value or values, so again, the foreshadowing. There might be more than one, possibly, of any horizontal tangent lines to that graph. This is a typical free response type question. They just tell you what to do, and you have to go out and do it, which means you have to know all the steps to take and all the notation to show. Horizontal tangent line. So start with the end in mind and work backwards from there. What do we know about the slope of a horizontal tangent line? It's 0, right? And so now that I know I need the slope to be 0, we know that we can find the slope by using the what function? Big D, derivative. So I need to find the derivative equation and set it equal to 0. Yeah, okay. So now I'm looking at my equation here, and I'm noticing it's not solved for y, nor do I care to solve it for y. No big deal. We'll find the derivative how? Implicitly. Good. And we take the derivative with respect to x on both sides. Okay, so let's do inventory first. How many y's do I have in this problem? 2. How many dy dx's should I end up with? 2. All right. First term, 2x squared. Derivative is, with respect to x, 4x. dx. Do we need that? No. Can you put it if you want to? Sure. The next one's going to require the what rule? Product rule. Good. So parentheses. The derivative of x with respect to x is 1. And again, you don't need to put that, but in this case, I like it for inventory purposes. So it's 1 times y plus x times the derivative of y with respect to x, which is dy dx. Good. So that one factor, again, generated 2 terms. I know everyone here knows the product rule, but this is the type of scenario where I see students forgetting the product rule. It's kind of just an interior term or an implicit differentiation. It's not just a straightforward product rule problem. And you have x's and y's instead of 2 functions of x. But just keep that in mind. Product rule. All right, so then we're back to just 4 times y squared, and that'll be 8y times the chain rule, dy dx, right? And don't forget the derivative of 3. What's the derivative of 3? 0. Yeah. Okay, so now I need to solve for dy dx, and I see that I have 2 terms that have dy dx in it. They're already on the same side, so I'm going to leave them on the left side. The other stuff in the front without a dy dx is going to go to the right side. And what would be the next step then? How do we get a dy dx by its lonesome? Divide it out, factor it out, right? And we're left with an x plus 8y. And then the other 2 terms, negative 4x minus y, go to the other side. So now the hard part's over. The algebra is kind of easy from this point. You just divide. And again, you could factor that negative out front, but I wouldn't recommend it. Did I leave out an x? Okay. Hang on. Oh, I sure did. Thank you. Thank you. Thank you. Thank you. Thank you. Okay, so now that we have the derivative, the correct derivative with that x in there like it's supposed to be, now I got to go back up here and remind myself what the heck I was doing, right? I was looking for the horizontal tangents. So I need to set the derivative equal to what? 4? 0. Yeah. Is it important to show that? Yeah. So dy dx, and again, you could say equals 0, or you could say 0 over non-zero, whichever you prefer. It is a quotient. The next line after that, you're going to go ahead and say negative 4x minus y equals 0. Now, looky there. We're kind of back in the same situation we were on the previous problem, right? On the last part, we have one equation with 2 unknowns. What do? Solve it for either variable. Now, which variable is easier to solve for? Definitely the y. Definitely the y. So Let's go ahead and make things easy for ourselves and solve it for the easier of the two variables. That right there then is something that we're going to plug back into the original expression, or the original equation, and you got to do this very carefully as well. So we get 2x squared plus x times y, which is now negative 4x, plus 4 times y squared equals 3. Plugging that back in up here. And then we carefully evaluate it. Everything is careful at this point. Negative 4x squared we get. And then negative 4x quantity squared gives us a positive 16x squared. And then 16 times 4 is? 64. Yeah, so be careful, be careful, be careful. Go off to the side and multiply things if you need to. No one's going to fault you for that. Now, the way that these problems are designed, if it's a non-calculator problem, they should work out so that they're solvable. And if you notice in this case, we have 3 like terms, don't we? They're all x squareds. So we can just combine their coefficients. 64 minus 4 is 60, plus 2 gives us 62x squared equals 3. And I think I've got it now. If I divide through by 62 and take the square root, I get plus or minus the square root of 3/62. And I'm happy with that. Now, did we answer the question? Did the question ask us for the ordered pairs? Did it ask us for the y values, or did it ask us for the x values? It asked us for the x values. Did we find the x values? Yes. Okay. Now, if they did ask for the y values, how would you find them? Yes, you could either plug it into y equals negative 4x or way back up there into the original relation. No thank you, original equation. I'm just going to plug them into that one. So then you'd have the option of plugging back into either. Now, the way that these problems are, again, also set up, not only are they solvable, but they're going to kind of design the question so that you're going to be finding typically the variable that is easier to solve. Remember, way back up here, it was easier to solve for y than it was for x. They kind of encouraged that by creating that question. So if you solve for y, that means when you plug in, you're going to have x's in your equation, and they're going to ask you to solve for x. All right, now I'm going to have you do B. I'm going to help you set it up, but I'm going to have you go through all the algebra. And while you're doing that, I'm going to get the decimal versions of these answers and plot them on the graph so that we can get some closure. Yeah? All right, determine the y values. Oh, that's different. We just found x values. Now we're looking for y values of any vertical tangent lines to that graph of that. Vertical tangent lines. What are we going to show? Our equation setup. dy dx equals non-zero over 0. Good. We want it to be D and E, but we want it to be D and E for a very particular reason. We want it to be an infinite slope, not a holy slope, right? That'd be 0 over 0. Once you show that, then we just set the denominator equal to 0, and I think y'all know what to do from this point, okay? So go for it. I'm going to get the decimal. Is it charged? Oh. Let me see it. Mind if I drop it and step on it? Okay. It had a battery drain. Yeah. It's critically low. Yeah. Did you? Yeah, it's critically low. There might be a ghost in here. Ghosts are known to draw energy from other sources. Huh. Do you have a charger on you or with you? No? All right, let's see how you did. Some of you are right there. Easier to solve for x, right? Everyone agree? So when you solve for x and then you plug in for every x with a y, you're going to have an equation in terms of y. And which one did they ask us to find? The y value. So that's a typical thing. And then when you carefully plug in and square things correctly, you end up with like terms again in terms of y. 124y squared equals 3. So y is equal plus or minus the square root of 3 1/24. And that's where you would stop. There's two answers. Now that's equal to about 0.15 if you're interested. And up here, the x-coordinates were about 0.219. So what I did is I came up here, and I looked. The scale here is 0.1. So if you go to like negative 0.2-ish and go up, there you go. You have your horizontal tangent. Spot right on the money. Spot on. Positive 0.2. I didn't write the 0.2. And go down, you get another horizontal tangent. And then we knew the y values were about 0.15. So if you go up to 0.15 and go to the left, there you see your vertical tangent, and then by symmetry you go down and go across, and you see that you have your vertical tangent. So we didn't find the accompanying x values for the vertical tangents or the y values for the horizontals, but we could. We could. The point is still to illustrate that we can find information analytically from a graph without actually having the graph, and now we can trust our methods. All right, any questions on this one? Fun? Yeah? So much fun, yeah. This is about the most fun algebra that we'll do all year long when you do this implicit differentiation stuff. It's kind of fun, and it's not that bad. We'll have some more fun algebra when we get into polar derivatives. There's some really good algebra involved there with trig involved, so it's like double fun. Yeah, like George Orwellian fun, like double plus good fun. All right, I'm just going to let you take the reins here on example 9, because y'all know what to do, right? Determine the equation of the tangent line to this equation at the point 3, 1. What do you need for the equation of a line? Slope and a point. Well, guess what you were given already? The point. All you need is the what? Slope. You're halfway there. Go. Yeah. Start. Yeah. You're halfway there, but you're not at the halfway point. Parentheses, though. Yeah, you were going to come back and do this, right? You were going to come back and do those without me saying, right? You were going to add parentheses if I hadn't said anything? Okay. Now this one's not quite done. It's 2y times dy dx. Yeah. Chain rule. Yes, chain. Chain, chain, chain. Chain rule. Lovely. Huh. Now remember, on this one, you have the option. You're after the numeric value of the slope. So you want to plug in and then simplify, or simplify and then plug in. That's your prerogative, as Bobby Brown would say. And no one knows that song. But y'all know who Bobby Brown is? Yes, yeah. The singer, right? The ex-husband of Whitney Houston, and father of the ex-singer. Yes, that's sad. Yeah. They were both at the top of the game at one point, and then. Right, problems. Mm-hmm. Hi, Coach Fair. You want to say anything for the YouTube video? Can I? Oh yeah, because the instructions. You're just trying to find the equation of the tangent line at the point 3,1. There you go. Now we can see 3,1. Dun, dun, dun. Dun, dun, dun. Have a good one, Coach Fair. Hi, Kate. All right. Maybe you're well on your way. I'm going to try and catch up with you here. I put d dx to both sides. When I walk up to the left side, I see 3 blobs squared. That's chain rule, right? So I don't even really know what's on the inside yet. Wink, wink. I just know the derivative of 3 blobs squared is 6 blob to the first, right? And I'm just going to rewrite the blob. I have to know what it is to rewrite it. But now I go inside, I'm like, it's an x squared plus y squared. That's 2 terms. So when I take the derivative, are the parentheses kind of important or not really? Yeah, kind of important, right. So the derivative of x squared becomes 2x times dx dx, which we don't need, plus y squared becomes 2y times dy dx, which we do need. And over here, on the right side, I have the what rule? Product rule. So as we do this implicit differentiation, all those rules, power rule, product rule, quotient rule, and chain rule, they're still viable. So we got the derivative of 100x is 100 times y plus 100x times the derivative of y with respect to x, which is dy dx. All right, decisions, decisions, decisions. If I'm going to solve this for dy dx first and then plug in, I need to get my dy dx terms together so I can factor it out. The guy on the right is expanded. He's a term. He's floatable. He can go from left to right or right to left. This guy, though, unfortunately, is trapped on the inside, right? He is part of this ginormous single term that is partially factored. So if you want to get your dy dx terms together, you would have to distribute this right here. Now, seeing that, what I would do at this point is I would just say at the point 3, 1, and I would plug in a 3 for every x and a 1 for every y so that things can start combining a little bit more quickly. But having said what I would do, I'm not going to do it that way because I want you to see what the algebra looks like with the symbols, okay? You would have to distribute this wonderful thing here inside to both terms. So you're going to have 6 quantity times 2x. That's going to be 12x times the quantity. And there's no need to distribute that. And then you're going to have 6 quantity times 2y dy dx, which will be 12y dy dx times the quantity. So I'm just leaving that x squared plus y squared acting as a single factor unit. And then, of course, over here you get 100y plus 100x dy dx. Now I'm able to get my terms with the dy dx on the same side and everything that doesn't on the other side. Now I'm going to do a 2-for-1 deal here. When I bring the 100x dy dx to the left side and got that other highlighted term on the left to the right, the next step would be to what? When you have your dy dx terms together, factor it out. So I'm going to factor my dy dx out, and that's going to give me a 12y x squared plus y squared. That is still on the left side, and then minus 100x. And that's going to equal the 100y that stayed over there minus this 12x x squared plus y squared that comes across. And then finally, dy dx would equal that wonderful thing over there, which you just arduously rewrite over that ginormous factor, and you have your nice derivative. So this is how I would not have done it in this particular case, but I did want you to see the algebra because sometimes you do have to distribute giant factor quantities inside of terms and carry around a lot of symbols with you. To evaluate it at 3,1, we would just say now dy dx evaluated at the point 3,1, and of course then we can just plug in a 1 for every x and a 3 for every y. And does anyone have the answer? Anyone get it? Let's see, you get 100 minus 36 times 3 squared plus 1 squared is 10, all over 12 times 1 is 12 times 10 is 120 minus 300. So you get 100 minus 360, which is negative 260, over negative 20 minus 300, which is negative 180. Your zeros divide out. Your negatives divide out. 26/18 comes out to be 13/9, and there's your answer. Now, I would have done that again way back up here after I did the second line, and I think that it would have worked a lot easier. All right, so we were able to finish that. There's one problem left. It's the second derivative implicitly. That's going to stay on the notes until Monday. We'll quiz on Monday, like the warm-up. Maybe have you find a horizontal or vertical tangent coordinate. We'll finish the notes, and then I'll give you that test on Tuesday. Yep. Hey, de nada.